Good afternoon, CM 440. We are Group 14, and our group members are Daniel Bent, Brandon Broussard, and Gavin Gautreaux. Today, we are going to explore the rapidly evolving topic of robotic bricklaying and how it's shaping the future of construction. This presentation will provide an overview of how these structures work, their benefits and challenges, and their impact on labor and construction efficiency. We'll also look at real-world examples like the Hadrian X and the SAM 100 systems. Let's get started. So, what is robotic bricklaying? Robotic bricklaying refers to the use of automated machinery and artificial intelligence to handle the task of laying bricks traditionally done by skilled masons. These machines are programmed with architectural blueprints and use robotics, software, and precision sensors to place bricks quickly and consistently. The main goal is to increase efficiency, improve accuracy, and address the growing shortage of skilled labor in the construction sector. By eliminating fatigue and human error, robotic systems offer a scalable and repeatable solution for modern building projects. Moving on, we're going to cover the core technologies involved in robotic bricklaying. At the heart of robotic bricklaying, there are several key technologies. First, CAD, which stands for Computer Aided Design software, translates architectural plans into machine-readable instructions. Robotic arms, mounted on mobile platforms, follow these instructions to lay bricks precisely and accurately. Automation algorithms ensure each movement is optimized for speed and accuracy. These systems also rely on real-time processing and feedback loops to adjust their actions as they go, ensuring the quality of the build throughout the process. Moving on, supporting systems. Robotic bricklaying wouldn't be possible without advanced support systems, such as cameras, lasers, and other sensors that scan the environment and adjust for inconsistencies or unexpected obstacles. GPS and LIDAR provide positioning and navigation, especially in the outdoor environments where terrain can be uneven. These systems allow the robots to know exactly where they are on the job site and exactly where each brick needs to go. Some platforms even integrate drones to map job sites and validate the robot's performance against the original plans. Workflow of robotic bricklaying system. The typical workflow starts with uploading the CAD file into the robot's onboard computer. The system then processes the file to determine the most efficient path and sequence for laying the bricks. Mortar or adhesive systems are preloaded and coordinated with brick placement to streamline the building process. As the robot operates, it uses real-time sensors to confirm the alignment and spacing. Operators monitor progress via a dashboard software and can make adjustments as needed, ensuring minimal downtime. One of these robotic bricklayers is Hadrian X, which was developed by Fast Brick Robotics, a company in Australia. It is a commercially deployed robotic bricklayer. It's mounted on a truck and uses a telescopic boom to lay bricks with exceptional speed at over 1,000 bricks an hour. One of its standout features is its dynamic stabilization technology, or DST, which allows the system to compensate for external forces like wind or movement, maintaining placement accuracy. It has already been used in several housing projects and demonstrates how this technology is not just theoretical, it's actively changing the construction industry. So to wrap up the first section, robotic bricklaying is an innovative blend of robotics, AI, and construction science. It offers a smart, scalable alternative to traditional masonry with potential benefits ranging from labor relief to enhanced build quality with real-world machines like Hadrian X, proving the concept. The foundation has been laid, literally and figuratively, for broader adoption in the industry.
Hello, I'm Brandon. The first thing I'll be diving into is the speed and productivity. One of the most notable advantages of robotic bricklaying is its impressive speed and productivity. While a skilled human or mason can only lay between 300 to 500 bricks in a full day, robots like Hadrian X can exceed over 1,000 a day. Or over 1,000 in just an hour, sorry. This level of efficiency is transformative for large-scale projects where deadlines are tight and time is money. Additionally, robots don't require breaks, don't get fatigued, and can work extended shifts with only minimal supervision. This enables continuous production and further shortening construction schedules. Precision and consistency. While precision and consistency are critical in construction, particularly for structural stability and aesthetic quality, robotic bricklayers use lasers, sensors, gyroscopic stabilizers, and advanced algorithms to ensure that every single brick is laid exactly where it needs to be. This eliminates human error such as uneven walls, misaligned joints, and not only does this reduce the need for rework, but it also improves the integrity of each structure that it is built. Every layer of bricks is uniform, improving both the strength and appearance of the finished product, which is also a good thing. Let's see. Safety benefits. Robotic systems significantly enhance job site safety by reducing the need for workers to engage in physically demanding and repetitive tasks. Bricklaying traditionally involves lifting heavy loads, repetitive motions, and working from scaffolding, all of which can contribute to injury risks. By shifting these tasks to machines, companies can reduce the occurrence of skeletal disorders, fatigue-related accidents, and falls. Workers are able to take on less dangerous roles like monitoring the equipment or programming its tasks instead of being in the field, which improves overall safety while maintaining employment. Cost savings long term. Though the upfront cost of purchasing or leasing robotic bricklaying systems is high, these machines can save money over time. Labor costs decrease as fewer workers are needed for manual tasks, and project timelines are shortened thanks to increased productivity. Additionally, material savings from reduced waste and rework contribute to the overall financial benefit of using robotic bricklaying. The faster completion time also means reduced overhead and earlier revenue generation for projects. Companies often find that the return on investment becomes clear after only a couple projects. Environmental considerations. Automation can contribute to more sustainable construction practices. Robotic systems reduce waste by applying mortar and placing bricks with exact precision, minimizing excess material use. Their operational efficiency also means less time spent on site, reducing emissions from supporting vehicles and machinery. In addition, the streamlined workflow can integrate with other eco-friendly technologies like modular construction and low-emission materials, helping companies meet green building standards and certifications. So overall, to summarize Section 2, robotic bricklaying offers a wide range of advantages over traditional methods, including increased speed, improved accuracy, and enhanced safety and long-term cost effectiveness. These machines are also more environmentally friendly by design. Together, these factors make robotic bricklaying an appealing option for forward-thinking construction firms looking to stay competitive in an industry facing labor shortages and increasing demand.
My name is Gavin, and I will be talking about the high initial investment of robotic bricklaying. One of the biggest hurdles of adopting robotic bricklaying systems is its initial financial cost. These machines can range from anywhere from $500,000 to over $1 million, depending on the capabilities and accessories. This high barrier to entry makes them inaccessible to small and medium-sized construction firms, especially those operating on tight margins. While there are long-term savings, the capital required upfront includes not just the equipment, but also the cost of training personnel, including maintaining the machines and adopting workflows to integrate the robotic process. The technical complexity is another issue with robotic bricklaying. Operating and maintaining robotic bricklaying systems requires a specialized skill set. Technicians must be trained in robotics, programming, and troubleshooting complex equipment. If a robot breaks down or a software glitch occurs, project progression can grind at a halt. Moreover, most construction sites are not currently optimized for robotic integration, requiring extra planning and adaptation. These challenges mean that adaptation is not just about buying the machine. It involves a fundamental shift in how construction firms operate. Site adaptability issues. While robots perform well in controlled, spacious, and flat environments, they struggle with more complex or confined job sites. Urban infill projects, historical renovations, or sites with difficult terrain can be problematic for robots to navigate. Additionally, unusual wall shapes or custom architectural details are difficult to execute without extensive reprogramming. The robots are optimized for repetitive tasks, not one-off designs, which limits the current flexibility and general application in many types of construction. The legal landscape has not yet fully caught up to robotic construction. Building codes, safety regulations, and liability frameworks are still primarily written with human workers in mind. This creates uncertainty around permitting, inspections, and insurance coverage. In the event of a malfunction or failure, it is unclear whether the manufacturer, operator, or contractor would be held responsible. Until clearer standards are developed, legal ambiguity will continue to hinder the widespread adoption of construction robots. Robots do not operate in isolation. They must work alongside human workers or other trades on the job site. Seamlessly integrating a robotic bricklayer into an active construction project requires careful coordination with subcontractors, deliveries, and supervisors. The construction schedule may need to be adjusted to accommodate the robot's workflow. Additionally, successful integration often requires the use of digital tools like BIM, Building Information Modeling, to plan and manage construction processes in a way that complements automation. Despite the promise of bricklaying, robotic bricklaying, there are legitimate challenges that must be addressed. The high cost, operational complexity, adaptation limitations, and regulatory uncertainty all pose barriers to entry. However, these are not insurmountable. As technology advances, training becomes more widespread, and legal frameworks evolve, we can expect these barriers to diminish. For now, early adopters serve as test cases, paving the way for the broader adoption in the years to come.
Workforce reduction. The introduction of robotic bricklaying systems naturally raises questions about job displacement in the construction industry. As machines take over repetitive tasks like laying bricks, fewer human masons are required on site. This can lead to reduced demand for traditional labor in the short term, especially for entry-level positions. However, it's important to recognize that this shift mirrors many historical transitions in labor markets driven by automation. While some roles may be eliminated, others, particularly those involving oversight, maintenance, and programming of these systems, are created. The focus is gradually moving from a physical labor to technical and supervisory skills, requiring change in how we train and deploy our workforce. The rise of tech roles. With the adoption of robotics, there is a clear rise in the demand for tech-based roles in construction. These include positions like robotics technicians, machine operators, software developers, and even data analysts. Rather than laying bricks by hand, future construction workers will be expected to interact with sophisticated machines, managing software interfaces, and interpret sensor data. The rise of these roles offers an opportunity for higher wages and more career longevity. Especially in a field that has traditionally been physically taxing, upskilling workers to fill these roles is essential to ensure the industry continues to grow while providing meaningful employment. Training and reskilling. To prepare for this shift in workforce needs, substantial investment must be made in training and reskilling programs. Trade schools, unions, and private companies are beginning to offer courses on automation and robotics in construction. These programs focus on helping current workers transition from manual roles to supervisory or technical positions. The future of construction lies in hybrid teams that include both skilled tradespeople and tech-savvy operators. Training workers to understand both sides of this equation will be essential for maintaining efficiency and safety on future job sites. The social and economic impacts. The social and economic impacts of automation in construction are complex and multifaceted. On one hand, automation can lead to job displacement, particularly for low-skilled workers. On the other hand, it can raise overall productivity, reduce costs, and make housing more affordable by speeding up construction. This tension highlights the need for balanced policymaking. Governments and companies must work together to provide safety nets and opportunities for displaced workers. Done right, the shift to automation can actually enhance economic mobility by opening doors to new, higher-paying careers in tech-enabled construction. To wrap up Section 4, robotic bricklaying will undoubtedly reshape the labor landscape in construction. It will reduce the need for some traditional roles while creating demand for a new wave of tech-oriented positions. The transition may be disruptive in the short term, but with proper planning, training, and support, it offers a more sustainable and advanced construction workforce for the future. The key is to not resist change, but to prepare for it and ensure no one is left behind.
Okay. I'm going to talk more about the Hadrian X. The Hadrian X was developed by Fast Brick Robotics in Australia. This is one of the most well-known and advanced robotic bricklaying systems in the world. The system is mounted on a truck and utilizes a 30-meter boom arm to place bricks with millimeter accuracy. What sets Hadrian X apart is its ability to work continuously, even in variable weather conditions, thanks to its dynamic stabilization technology. In field tests, Hadrian X has been able to construct the walls of a standard-sized home in just a couple of days, showcasing its speed, precision, and reliability. This case study proves that robotic bricklaying is not only viable, but scalable in real-world construction and projects. Another case study that was on the SAM 100. The SAM 100, short for Semi-Automated Mason, was developed by Construction Robotics in the United States. Unlike Hadrian X, SAM 100 is designed to assist rather than replace human workers. It's a bricklaying robot that works alongside masons by lifting and placing bricks while the human worker focuses on the quality and control and finishing touches. SAM 100 has been used in commercial projects such as schools, hospitals, where repetitive wall structures are common. The machine can lay up to 3,000 bricks per day, improving productivity and reducing physical strain on workers. It represents more of a hybrid future where humans and machines can collaborate to achieve optimal results. Some of the key lessons from these studies illustrates the future of automated construction. First, full automation as seen with Hadrian X, is ideal for projects that demand speed, repetition, and minimal customization. On the other hand, semi-automated systems like SAM 100 show that there's still a valuable role for skilled labor, especially in tasks that require judgment or adaptability. Both systems highlight the importance of planning, training, and integration with other job site activities. Ultimately, these examples demonstrate that robotic bricklaying is most effective when used strategically on project type, site conditions, and labor availability. Future projections. Looking ahead, the future of robotic bricklaying appears promising as technology continues to advance. We can expect robots to become even more affordable and capable of handling more complex tasks and integrating these with new technologies. So to summarize section 5, Hadrian X and SAM X shows us that robotic bricklaying is not a distant concept and is already being used successfully in the field. These case studies provide a roadmap for how companies can adopt and benefit from this technology. By understanding where automation works best and how to integrate it effectively, firms can unlock new levels of productivity, safety, and cost efficiency using these systems.
The final summary: robotic bricklaying is reshaping how we think about construction. It provides a solution to multiple industry challenges, including labor shortage, slow project timelines, and inconsistent quality. The benefits, speed, precision, safety, and cost efficiency, are compelling, but as we've seen, challenges around cost, complexity, and labor transitions must be addressed. Real-world implications such as Hadrian X and SAM 100 show that the technology works and it is gaining traction. Moving forward, the key will be managing change through policy, education, collaboration between industry leaders and labor advocates to ensure that automation enhances rather than disrupts the construction workforce. References. Our research and insights for this presentation were based on the leading sources in the field of construction automation. These include publications such as the Journal of Construction Engineering, the Automation and Construction Journal, and the reports from Fast Break Robotics and Construction Robotics. We also referenced IEEE transactions on automation science and engineering to understand the broader implications of robotic systems in the industrial setting.